Hello everyone, Jim Malis again. Just got to talk to you about something real quick here. I'm looking to do problem number 41 from chapter 6 again. I am going to delete it from part of a previous video, and we're going to try to graft what I'm doing right here into the previous video. So when you're looking at the video, you'll be hearing me saying this, and you'll know why things look a little bit differently. To make a very long story short, there was the answer key in the book, and apparently the solutions manual as well. But certainly the answer key in the book is incorrect. The problem was done wrong. I looked at how they were doing it, but I didn't pay too close attention to it, so I took it at face value. So I also made the mistake by accepting what was done in the book. When the book had done it wrong. I was also wrong to accept that. So my fault as well. With the huge number of problems that the people that are writing these textbooks have to do, on occasion they're going to make a mistake. That's a human thing. I mean, we all make mistakes, every one of us. So they made a mistake on chapter 6, problem number 41. Problem number 41 from chapter 6 was done wrong in the answer key. Let me do it, or at least give you an argument as to how it's supposed to proceed the right way to go. Essentially, they're saying for problem number 41, chapter 6, an inflated spherical beach ball with a radius of 0.3573 meters and an average density of 10.65 kilograms per meter cubed is being held underwater in a pool by Janelle. The density of the water in the pool is 1,000 kilograms per cubic meter. When Janelle releases the ball, it begins to rise to the surface. If the drag coefficient of the ball in the water is 0.470 and the constant upward force on the ball, because of the buoyant force, they don't say that here, but that's what it is, and the constant upward force on the ball is 1,875 newtons, what will be the terminal speed of the ball as it rises? Ignore the effects of gravity on the ball. So there is a beach ball immersed in the water. There is a buoyant force going upward, and there is a drag force going downward. Once you reach terminal velocity, the buoyant force will be equal to the drag force. It's that simple. They are telling us a number of things. They're telling us that the ball, spherical ball that it is, has a radius of 0.3573 meters. It's the radius of the ball. They are telling us that the density of the ball, so in other words, has an average density, I mean the plastic out of which the ball is made and the air that is surrounded by the plastic, all told, the density of the ball, is 10.65 kilograms per cubic meter. The density of the water under consideration is 1,000 kilograms per cubic meter. There is a drag coefficient, capital C, unitless quantity, 0.470, and there's a constant upward force of the ball. That constant upward force, you guys, though they don't tell us that explicitly, is the buoyant force. There's a constant upward force on the ball of 1,875 newtons. Ignore the effects of gravity on the ball. When they're saying ignore the effects of gravity on the ball, the density of the ball, and this is maybe not the best way to say it, the roll of the ball means the roll of the ball, meaning the plastic surrounding the ball and the air that's inside the ball. Put the air, put the plastic, put them together. If you find out what the mass is of the plastic and the air together, find out that mass and divide by the volume, you get the mass density of the ball and air. the ball and air density is this. Well, they told us don't concern ourselves with the gravitational effects that the ball is experiencing. Ignore the effects of gravity on the ball. So this is almost here to throw you off. In the actual answers that they gave in the book, and they gave at the the answers that they gave at the back of the book, they somehow brought the ball in there in such a way that really made no sense. Not trying to be self-righteous about the whole thing, guys. I also made the mistake by accepting it. I should have looked at it much better. That's my fault. I copied it down without looking at it carefully. I usually don't do that. This time, apparently I did this time though, right? So it was my fault for doing something I usually don't do when I'm writing this stuff down. It has to make sense to me. Perhaps I was rushed. I don't know. My fault. And they also, like I said, they did make a mistake. Now, with the thousands of problems that get done on occasion that these people do, I mean, with just the multitude of problems that they do, on occasion something can go wrong. Somebody can make a mistake. And that can happen to anybody, as we said, guys. So there it is. I mean, they're same size when you reach the terminal velocity. What's going on here? Well, I got to talk to you a little bit before we even go there. They don't talk about this. They don't talk about this in their, anywhere in the solution to the problem. But I think we should look at it. Isn't the buoyant force, according to Archimedes, equal to the weight of the displaced fluid? Period. The weight of the displaced fluid is the buoyant force that the ball is experiencing. What is the weight of the displaced fluid? It's mass times g. Well, what's the mass? What's the mass of the water? Well, the buoyant force is going to be the mass of the water that was displaced times g, and that's it. Basically, I should say that the mass of the water that was displaced times g. Well, what is that? Let's talk some more. What do you say you find the mass density of water? The mass density of water times the volume of the ball. The volume of the ball will tell you the volume of the water that is displaced. The volume of the water that is displaced times the mass density of water is the mass of water that's displaced. The mass of water displaced times g will be the buoyant force. Pretty neat. If we do the mass of water, let's bypass the units for now. Let's make sure the units are right at least. At least we're consistent with units. The mass of the water, the mass density of the water is 1,000 kilograms per cubic meter. The volume of the water that is displaced is the volume of the ball. It's that. Okay, pretty interesting that way. The G typically in our 209 class and in Katz's book, they're using the G to be 9.81. So kind of watch your step on something like that. What's going on here? Well, this thing right here, we're essentially going in this direction. We're saying 1,000 times 4/3 times pi times 0.3573 cubed. That's meters. 0.3573 cubed. That's meters. Times 9.81. When you actually do it, it comes out to like 1874 point something. Comes really close to the ballpark of what they're talking about. So I don't, I'm not going to nickel and dime them on that, you guys. They kind of cut to the chase and told us that. What they told us is accurate. It's off. It's off by if it's not real accurate, it's off by less than 1. It's like 1874 point something. It's off by maybe 0.6 something like that. 0.6, 0.7. according to the calculations, according to what they're saying. That's not a big deal. 0.6 or 0.7 out of 1875 is not a whole lot. So it came out about 1874, something along those lines when we actually do it. Let me just, yeah, there it is. Just for the sake of argument, I'd done it with the other one too. Let's see what we can say here. 0.3573 times yeah, I got, somewhere, assuming I'm kind of rushing it, guys, here. I got 1874.3757, 1,874.376, thereabouts. 1874.376. I told you, it wasn't off by much. In terms of newtons, and we'll say that. So what they had said, it's not bad, not a bad guess. Well, that would have been interesting to kind of look at. I mean, to kind of bring that forward. So we got that. If you're going to go that way, the whole thing, I guess you could say, kind of hinges on the following. You're looking at basically so guys, if we're looking at that, how are we actually going to solve a problem like this? It all hinges right about here. You're going to take it and you're going to say, because we're saying this, FB equals FD, we're essentially, there's a whole bunch of plays you can make on this thing, but you're going to say, or FD equals this, whatever you want to say. FD, we could kind of like put this over to the side, I guess you could say. This is rho H2O. Rho H2O, V ball, times G. That's FB. F drag, they've got a formula there they give us. We're going to go with it. I'm sure there's some pretty fascinating ways we could get derivations of it. They're not going down that road. Let's us not go down that road right now. Let's just kind of get a gut feeling for what's happening. This is 1/2. This is the capital C we talked about. That's the same capital C we got right here. 1/2 capital C rho AV squared. The rho is the rho of the fluid, not the rho of the ball, you guys. This one right here is going to be, so when you're doing this, here's FB, here's FD. So we're using this guy and we're using this guy to get it done. So what we're looking at is FB equals FD. FB equals FD. We got rho H2O, V ball, G, correct? correct? Equals 1/2. So let me give myself a little bit more room. So we got these. We've already said a few things here, guys. They gave us this. We've utilized this already. So you've got it on tape. Give myself just a little bit more room here. We're looking at this, and the other one's 1/2, right? So we got this and this, setting it equal. Equals 1/2 C, row of the fluid, guys, not row of the ball. In this case, the row of the fluid is the row of water. That's AV squared. The capital V is volume. The small v is velocity. Well, rho H2O and rho H2O are going to cancel. You can divide by rho H2O on each side. You can divide by rho H2O on each side, and solving for V, we got, well, let's go bits and pieces. Let's solve for V squared. Dividing by rho H2O, divide by rho H2O on each side, you got that. Multiply by 2 on each side, and divide by CA. Multiply by 2 on each side and divide by CA, absolutely. So 2 V ball G divided by CA. Now, we never really talked about what A was. A is the surface area perpendicularly in contact as it's moving through the fluid. I'm sure that I did not say that in the best way, so let me. Basically, they're saying there's a beach ball looking like this. Here's the great circle associated with the beach ball. Here's R this way. It's going upward this way, and they want to know what is the surface area that is in contact with the fluid as the item is moving through the fluid. As the object is moving through the fluid, what is the perpendicular, what is the component of area that is perpendicular to the direction of flow? What is the sum of all the minuscule, all the infinitesimal perpendicular areas? Areas that are all perpendicular to the direction of flow, to the direction of contact with the water. What they're trying to say here, guys, in an interesting manner is this. They want that area. That area, I understand that the area of a sphere, the area of a sphere is 4 pi r squared. The area of half a sphere is half of that, 2 pi r squared. True. I don't want either one of them. I want the area of the great circle. Doesn't look like that circle's hitting anything. Yeah, but that's what I want, and I'll tell you why. That's the area you want. That's the area they're talking about. The area under consideration is pi r squared. Essentially what's going on, you guys, is they want you to find what's that perpendicular area. What's that? What's that? What's that? What's that? This is obviously, by no stretch of the imagination, any kind of good drawing here, but they're saying find area that is perpendicular to the direction of flow. So sum all these perpendicular components up. Every one of these perpendicular components falls right down onto here. If you sum all these perpendicular components, you're getting this. That's the big thing right here. And this is where it's going to, that's what you got to have in there. So when you do that, you can, like I said, now we already solved it with the 1,000 as we said, all the stuff that we had already said. We'd solved this in a bunch of ways. We already kind of had, you could have said, hey, look, Malus, what are you doing? They already gave us the buoyant force. We just delivered a speech regarding the buoyant force, deriving some stuff. The buoyant force was in the ballpark of 1875, and then you got this business. The C, the rho H2O, and the V squared, and man, that's a whole lot easier to deal with. We already done that. We already found what the buoyant force was. We had that. And we could have gone with that as well. So either one is going to work okay, you guys. With this in mind, let's solve this. Let's solve it from right here. Let's take this guy. Let's go long distance. 1875 equals 1/2 C rho H2O V squared. 1875 newtons equals 1/2 C rho H2O V squared. And the V squared is V terminal velocity squared. That's what it means. When these are equal, you guys, when these are equal, that's it. When the buoyant force is firing up, when the buoyant force is firing up, and the drag force is holding it down, and the buoyant force shooting upward and the drag force pulling it back, when those are equal and opposite to each other, there's a constant velocity attained. That constant velocity is called the terminal velocity. There's no further acceleration. Why is there no further acceleration? There's no net unbalanced force. How is there no unbalanced force? Well, we already said it. If this fires, the drag pulls down, the buoyant force pulls up, you add them together, you do a vector sum of those together. The vector sum of FB vector and FD vector is zero vector. The buoyant force and the drag force are equal and opposite to each other. Zero net force means no acceleration. It reached the terminal velocity. It reached the greatest velocity it's going to reach in this particular circumstance. And it's as simple as that. So what does that mean? Well, that means here's the buoyant force. It means here's the buoyant force, and here is the drag force. It's exactly what it means. So if that's the case, what do we got? We got 1/2. C is 0.470. C is 0.470. Rho is 1,000. The terminal velocity squared is this. Let me multiply. Let's see what we got here. We got VT squared. Let me multiply by 2 on each side. Get 3750 right here. Let me divide by the product of these two, which is, okay, what did we do? What did we do here? We multiplied by 2 on each side, got this. We divided by this product. So if you multiply by 2 on each side and divide by this product, you got VT squared. VT is going to be this. This times this is 470. That makes it a little easier to look at. Square root it. Square root both sides. So you got to here, then square root both sides, as we said. The square root of the quotient, the square root of the quotient, 3,750 divided by 470. The square root of that quotient see what we got here. Yeah, it's very interesting how that worked out. Should be the same answer as the other one now. I don't want to get too far into this, guys. Let me just make sure I did something, make sure everything is right on this one, right? Yeah, there is something wrong here. We did not put the A in there. That's what's explaining that. Here I'm sanctimoniously preaching as to how they did something wrong. I'm looking to correct it, and I'm about to do it wrong. All right, let's see what's going on here, guys. This was up to there, and this had to be an A right here. This had to be an AV squared. All right, let's do it again. 1875, 1/2. Okay, that should be okay. 1875 equals 1/2 capital C. There's got to be an A. This is what we talked about from the beginning. I neglected the A and got an outrageous answer that I luckily did not report to you. A is pi r squared. That's terminal velocity right there. Tell you what I'm going to do. V terminal velocity is going to be the square root of a lot of stuff. You're going to multiply by 2 all the way across. You're going to divide by the product, C, rho H2O, and A. So what are we doing here? What is that? We got 3750. We got 0.4. The capital C is 0.470. The rho H2O is 1,000. Yeah, it's 1,000. A is pi r squared. Pi R is 0.3573 meters. Make sure all the units are green. You can bypass units, guys, if the units are in agreement. Squared. Okay, it's, a little bit of a mess, but okay. So, if that's the whole process, what is this coming out here? What is this coming out to? VT equals the square root of that mass. So let's see what that's going to be. So on this one, let's see, let's try it again here. Okay, let's just make sure we're in agreement here, guys, when we're doing this stuff. One second here, guys. All right, that's better. That's what I got in the initial correction that I had done in the stuff that we're erasing. So we got right about here. This is what it should be. This is the terminal velocity. This is as fast as it's going to get. 4.46, 024, 5383, whatever. 4.46, about 4.46. The book has just 0.46. And the way they had done it, the logic was not right. And by following that logic, I was equally wrong. So here's the correction for it. I'll try to put it in writing as well when we do that. Would you have gotten the same answer had you gone strictly with the symbolism and then gone for it? Say, hey, look, by the way, I mean, you're saying FB equals FD. FB is rho H2O, V of the ball, times G. That's going to equal 1/2 capital C, rho of the water, V of the ball. You got this right here. They put an A here, which is easy to overlook. There's enough of an alphabet soup over there, guys. You can get in some kind of trouble. Could you say, hey, look, this is rho H2O. This is V of the ball, which is 4/3 pi r cubed. This is G, and I guess we'll figure out what that is. That's 1/2. This is C. This is rho H2O again. This is pi r squared. We only care about the perpendicular phenomenon. What is this? This. I only care about the perpendicular component, how this stuff is hitting. Well, if you add all these infinitesimal areas, they don't see, if you had the areas going sideways like this, that's a different story. If you had the areas going sideways, if the areas were doing this, they're not, but if they were doing this everywhere in 3 dimensions, it would be 4 pi r squared divided by 1/2. Just the half sphere, the semisphere, the hemisphere, whatever. Hemisphere, semisphere. The half sphere would be half of 4 pi r squared, which would be 2 pi r squared. If I was talking about if I was talking about curving with the curve of the sphere. I'm not curving with the curve of the sphere, you guys. I want the perpendicular area of what's going on with that. So it's a different dynamic. And that's where this stuff came in. That's where all these came in like that. Like that. And that's coming right out at you too. It's coming out at you this way. And then all those areas. It's not just a circle, you're looking straight out at it. It's a 3-dimensional phenomenon. All those areas that are perpendicular to the direction of flow, they add up to, I guess, the shadow of all this, the great circles area, which is pi r squared. If you were going all the way around the curve, though, and I say, look, I'm going to put tile around the sphere, around half the sphere, area of a sphere is 4 pi r squared. For the half sphere, it's 4 pi r squared divided by 2. It's 2 pi r squared. But if I want the perpendicular, it's just this guy. It's just this. This is the projection of all those coming down that way. So if you're looking at it, like this, can we do it? Absolutely we can do it. This is, now I'm just doing straight non-numeric symbolism. I took FB is this, FD is that, rho H2O cancels with rho H2O. Pi cancels with pi. R squared cancels with r cubed, leaving you just an r. Multiply by 2 on each side, you get an 8 right there. So I'm just, we're just tinkering with this thing. doing a little mental gymnastics in the whole process, 4.46, it better be, should be close. Now we said it was going to be, we did a lot of stuff to get there actually in the past that I'm erasing and putting right here, you guys, but what do we got here? Why don't you multiply by 2 on each side, and you got 8 over 3, RG equals, what did we say here? We got this, we had the V squared right here. That's the terminal velocity. Right next to that, I failed to put that on there. Here it is, there. So we got C VT squared is 8RG over 3C VT equals the square root of what do we got? We've got 8, we've got 0.3573, and we got 9.81. I'm sorry, I just ran out of room there. Three times 0.470. Well, hope it gets in the ballpark of where I want to go. Let's have a look at it. I got 4.459. I got 4.4595. Close enough, guys. I mean, like I said, I think they rounded somewhere as well when they had done some of this stuff. That's not really the matter. The big thing here is we got it. Any way you go here. Now again, you don't have, I mean, the more you can knock out of there. And there you go. It's that. That's it. I mean, you could, there's I suppose a number of ways you could look at it. Essentially, the key to everything, ladies and gentlemen, the key to everything is FB equals FD, and then go for it. Okay. All right. That's what I'm going to try. You see it spliced. It looks different. I think it's different clothing than I had the last time I had done the problem. We're going to try to link it up to the problems that I had done with chapter 6. Okay. If not, you see it as is, and I have it right here. Okay. All right. Thank you much. Take care.